Restricting domains of functions to make them invertible and uses of invertible functions. Now, in my last video, we talked about I can convert a function that is not invertible all the way across to invertible within certain boundaries. That's what we're talking about today. We can use the horizontal line test. Now, the vertical line test tells us if it's a function. We use a horizontal line test on the original function to determine if it's invertible or not. For example, if I have a parabola, and so I'm going to draw a quick one right here. Now, it's a function because it passes the vertical line test. By using the horizontal line test, and as we looked at before, when it's invertible, it does not pass vertical line test. But if I use the horizontal line test on the original function right here for this parabola, I don't have to go any farther. It's already passed through this twice. So we know that this y equals x squared is not an invertible function. And we're going to restrict some of these domains, the x's, to see when we can and cannot have an invertible function. Now these are all invertible functions. Notice the horizontal line test passed through and any area only once at y equals x, right here, y equals x cubed, and y equals 1 to the x. Notice these are not invertible functions. We use the horizontal line test. Y equals x squared, it passes through more than once. Y equals x cubed plus 3x squared, it does pass more than once, actually 3 times in a few areas between, looks like, where y equals 4 and y equals 0. And then I got sine waves, is actually y equals, so a cosine wave, y equals 5 cosine of the x. And this is not an invertible function because it passes through multiple times. Now, how do we can make this invertible? Well, we can restrict the boundaries here. This has passed through more than once. But how do I use the horizontal line to determine where it can pass through only one time? By restricting the boundaries here. For example, from x equals 0 to x equals 6.38, that's actually 2 pi right there. A horizontal line test will only pass through once at any point here. So I could say this invertible function between 0 and x equals 0 and x is 6.38. Now, can we do this with a parabola? Yeah, we can make it so the domain only goes from 0 to infinity as I've darkened here. So only this part. Yeah, and if I did make it an invertible function, it would look like that because I would not include the other side. And that passed the horizontal line test. And we use vertical line test to determine if we can or can't. And like I said, if we restrict the domain, not all numbers, but only from 0 to infinity, as I got right here, in this direction, I can make this an invertible function. Real life uses of invertible functions. Topography. This is where the elevation depression on a topographic map. We want to convert 3 dimensions into 2. And what you see here is if x equals 120y, in other words, 1 inch equals 10 feet on this map for real life. And if y is 120x here. What I'm looking at here, you could see, based on this invertible function, well, I can determine the space between these two, how steep the slope is. If this y area is bigger between each thing, it is less steep. It's a slower slope right there. The higher up I go, the more steep it gets. Each one is 10 feet vertically, and we represent by the circle here. Here's a more gentle one. This is a wider space between each one of these, so this is a more gentle slope right here. Now, another use of invertible functions, look at invasive species. Invasive species, for people here from Georgia, includes kudzu. pythons and anacondas in Florida, which are not introduced. And the problem is all of these, the kudzu and the snakes, reproduce very quickly, better than the average native species do. And they keep reproducing, and they can overrun the environment. The general rule of thumb is these are invertible functions in the invasive species growth rate. And what happens is that it destroys the original species. And this is what happens right here, this curve right here. The original growth rate without a native species will go this blue line right here. Once you have an invasive species, it declines the native species. One of the most resilient examples of this is lampreys. Lampreys are very ancient creatures. They're the borderline between invertebrates and vertebrates. They don't even have a backbone. They have a notochord. And they look like eels, but they're really not. They're not fish at all. They're more ancient than that. They have this open mouth that has little barbed teeth, and they suck the insides out of fish, like this lake trout right here on the very left. These were only live in the ocean until they opened the St. Lawrence Seaway into the Great Lakes, and they invaded the Great Lakes and decimated the lake trout and salmon industry in the Great Lakes. To show you how old they are, here is the age of man, age of dinosaurs. This was the first ancient fishes. Lampreys were around this far back. And by the way, they're disgusting creatures. They actually, as a defense mechanism, you try to pick them up, they slime you. It comes out of their body pores. This destroyed almost 60% of all the lake trout and salmon coming into the Great Lakes, and diminished actually what was a great commercial fishing livelihood over the last 50 years. And the salmon and lake trout are among top predators, so that naturally in their environment, and so that affected the entire ecosystem. And you look at this, sea lampreys have killed more than 100 million pounds of Great Lake fish annually, which is 5 times the harvest in the upper Great Lakes, such as Lake Superior, upper Lake Michigan, Lake Huron. There's a thing called lampricides. 3 ways to control these things is by putting lampricides in, which makes them so the sea lamprey larvae, the babies, cannot fully go full growth, so they can't reproduce. Also, it barriers a lot of the tributaries, so it doesn't get into other areas right down. These are little fences. And then there's also traps they've set. And as you can see here, these have been very effective. And look at these graphs here. That's where the lampreys were before they started in each one of these. And they've gone down quite a bit. It is an active, ongoing thing. And basically it shows how these functions will, because they're invertible functions, will bring other native species back.